So what's done today is you engineer a virus. Once you have the virus, it's actually relatively easy. You engineer the virus, you let the virus incubate with the cells. The viruses, are naturally inclined to infect the cells. And then once those viral cells are infected, you remove any extra viral particles and you have your edited cells. In our case, you will take your cell that you're looking to edit, plus the payload that you're looking to upload into the cell, the gene altering material, and you flow both of them through our fluidic devices. And these devices apply a combination of fluid flow and electric fields to the cell in order to open pores in the cell and allow that gene editing material in. So we're physically opening the pores. We're using flow and electric fields to physically open pores and put that genetic material in that does the editing, such as CRISPR. Conversely, in the case of viruses, the viruses naturally attach to the cell and upload and integrate into the genome. And so you don't have to do anything physically, you just let them sit there. In our case, we are acting on the cells and payload in order to cause this reaction to happen. Yeah, so every technology that is being used to deliver material to cells, they really all do the same thing. So you have a cell, you put some kind of energy into the cell. Sometimes it's mechanical energy, sometimes it's electrical energy. And the cell responds by opening pores. Once those pores open up, foreign things can get in. So in mechanical methods, some use squeezing, some use high fluid flow rates. In those methods, they're putting mechanical energy into the cell. The cell responds to this stress by opening pores and things can diffuse in. In the case of classical electroporation, which is something that's been around for 30 or 40 years, you put purely electrical energy into the cell, so you zap them. The cell responds by opening pores, and then the gene altering material can get into the cell. The challenge with electroporation is that, shockingly, cells don't like being shocked, and a lot of them die, and how effective they are after the process, there's question in the field on how effective they will be for these therapies. But an advantage of electric fields is that cells actually have two membranes. They have an outer membrane and a nuclear membrane, and you can actually open both with an electric field. The challenge in mechanical methods is mechanical methods just act on the outer membrane. They don't act on the nuclear membrane. So you can get things into the cell, but sometimes delivering to the nucleus can be a little more challenging. But the advantage of the mechanical methods is that cells tend to respond better to mechanical stimuli compared to the electrical. So more of the cells are alive and their function seems to be a little bit better. The technology that we've been working on is really a combination, you might say, of both. We're adding mechanical energy plus electrical energy. And it turns out that the amount of electrical energy we deliver to the cell is a small fraction of what is done in the purely electrical cases. If you just used our electrical energy, you couldn't do the process. It's our electrical energy plus the mechanical energy that actually opens pores. And so you could think of it as we're reducing the electrical energy just enough to open the pores and get material into the nucleus, but not so much that a lot of the cells are dying and their health is affected. And so it's kind of like the best of both worlds. So trying to get the health of the mechanical systems, but still delivering to the nucleus, which is what you need to do if you're going to engineer cells for stable genetic engineering, where you want those cells to have an edit that'll persist for a long time. In our case, when we talk about mechanical energy, it's the force of the fluid flow, but I would actually there are many ways of putting mechanical forces in on the cell. So the fluid flow can impose shear stresses. You could physically do it by pressing on the cells. You could add pressure waves via ultrasound. That's another way of, I would say, adding mechanical energy into the cell. So there are multiple ways of adding mechanical energy. Ours is actually through the fluid flow. So we've developed an assay that allows you to quickly screen the electrical conditions, the minimal electrical conditions that would open pores in a cell. The theory being, once again, too much electrical energy was bad on cells. So could you figure out a way of finding that Goldilocks, what's just right enough to open pores but not kill a lot of the cells? So that's work we've done in the past, is using a microfluidic assay to rapidly determine the smallest amount of electrical energy we can deliver to cells.